Aloha friends! We will be solving a problem involving a transient response of simple control system. This problem will help us in further understanding the idea or the concept of a step response in a simple control system with a specific mode. In this problem, let us consider a thermal system controlled by a PD controller. This figure shows the three tanks, the PD controller, the Q, and the load entering at tank 1. Given also is this data, the flow rate, the density, the volumes, and the specific heat value. It should be noted also that the change of 1 psi from the controller changes the flow rate of heat by 500 BTU per minute. The temperature of the inlet stream may vary and there is no lag in the measuring element. These conditions must be noted for it would be helpful in establishing the energy balance. What we are required in this problem are the following. First, draw a block diagram of a control system with the appropriate transfer function in each block. Each transfer function should contain numerical values of the parameters. Second, from the block diagram, determine the overall transfer function relating the temperature in tank 3 thus change in set point. And third, find the offset for a unit step change in inlet temperature if the controller gain Kc is 3 psi per degree Fahrenheit of temperature error and the derivative time is 0.5 minutes. Heavy? Don't worry too much. I have prepared a simple solution outline to make the solution simpler. This will serve as a guideline in answering the problem. First, we generate energy balance, then we determine the parameters, draw the block diagram, use final value theorem in solving the offset, and Simulink to simulate the problem so that the answer will be verified and the conclusion will be generated then. Ready? We can now start solving the problem. We first establish energy balance in tank 1. By inspection, it can be observed that there are two inputs, the load and the Q. Letting Ti the inlet temperature of the load and T1 the temperature leaving the tank 1, the energy balance in this tank will be. Keeping C constant, it can be reduced into this equation. And at steady state, we'll have this equation. Since these two equations are from one system, we can manipulate by subtraction to produce this equation. We now introduce division variables, the Ti prime, the Q, and the T1 prime, and substituting into the previous equation, we get. This will be used to find the Laplace transform and proceed to determining the transfer function. Substituting the given values as well as the deviation variables, and knowing that there is a change in Qt only, then Ti prime of t is equal to 0, so we can get this transfer function relating T1 prime of s and Q of s. This be our first transfer function for the process. We now consider tank 2. Letting T1 as the temperature entering tank 2 and T2 as the temperature leaving the tank and V2 as its volume, we can have this equation and can be reduced into this equation. At steady state, this is the equation generated. Subtracting the two equations, we will get, providing deviation variable T2 prime and substituting it to the previous equation, we'll get Wt1 prime minus Wt2 prime is equal to the density V2 dt2 prime over dt. Getting the Laplace transform, the equation will be, and simplifying it to get the second transfer function, which will be the transfer function involving T2 prime and T1 prime. Tank 3 will be next, letting T2 the temperature input in tank 3 and T3 as the temperature leaving it. Establishing the energy balance will get this that can be reduced into this. At steady state, the expression will be subtracting the 2 we will get, introducing the deviation variable T3' and substituting it to the expression and reduced into WT2' minus WT3' is just equal to the density times the volume of tank 3 d3' over dt. Getting the Laplace transform and substituting the values will get the third transfer function relating T3' and T2'. These transfer functions we obtained will be used in providing the transfer function for the process, which will be included in the block diagram. After getting those transfer functions, we will now draw the block diagram. In drawing the block diagram, first, we establish the set point, determine the controlled variable, place the controller after the set point with a summing junction that connects them, and the feedback, adding the heat, Q, the disturbance, and the process transfer function. This is now our final block diagram, where PD controller represents Kc times tau ds plus 1 and Kp 1 over 250 all over s plus 1 multiplied by 1 all over 1.25s plus 1 times 1.5s plus 1. The first term refers to the transfer function in tank 1 and the second in tank 2 and 3. We can now determine the overall transfer function relating the temperatures in tank 3 to a change in set point. From the block diagram, we can generate this expression, or we can follow the shortcut method in finding the transfer function involving feedback. Simplifying, we'll get the overall transfer function relating T3' and a set point y. In finding the offset for a unit step change in inlet temperature given Kc 3 psi degree Fahrenheit and derivative time tau d 0.5 minute, we will use the transfer function relating T3' and T1'. The expression is this. Now, to solve the offset, we'll have to use the final value theorem, which states that the limit of f of t as t approaches positive infinity is also equal to the limit of f of s as s approaches 0. So, substituting the given values and evaluating its limit, we're left with the offset, which is equal to 0.1429. We are now done with the three requirements. Let us check our outline what to do next. We're done generating energy balance, determining the parameters, drawing the block diagram, and calculating the offset. Now, we use Simulink and simulate the problem to verify our answer and further develop a conclusion. We open the MATLAB, go to the Simulink, and create the model. I already constructed the model that represents the thermal system problem. As you can see, the source is a step input. It is connected then into the simplified PID block. It is preferred to use the simplified form to avoid fluctuations in the graph as to depend on the filters set when using the PID, the actual PID block. The blue one is for the proportional with 3 as the gain, 0 for integral since it is a PD controller, and the time derivative is 0.5 for the derivative part. Input Q is present, which is equal to 500, as well as the process transfer function in tank 1, 2, and 3. The disturbance was kept 0 to obtain a servo problem. So, with a running time of 100, we graph it, and we'll have to determine the point in which it approaches close to the set point. Okay, we just have to keep on zooming to obtain at least 4 decimals value, which would verify what we have calculated earlier. So I think 0.8573 would be enough. So the graph shows oscillations at first, but after some time it constantly attained stability and became nearer to the set point. Since only the offset is to be verified, we'll stick to it and it will be verified later on. As we can see, using Simulink and graphing it, we were able to get the value of a controlled variable at a specific time when it approaches near to the set point, noting it to be the offset. So from the graph, the offset will be 1 minus 0.8573, or it is equal to 0.1427. Comparing it to the calculated value 0.1429, the results are close enough. Therefore, this Simulink can be a good tool for verifying the calculated values, so as to lead you of whether you are on the right track or not in solving these control system problems. Furthermore, simulating problems like this one will make it less difficult if you have to model it, and you will be able to simulate it in Simulink. That would be all for today. Thank you for viewing, and I hope you learned something. Bye!